Good morning, dragons. All right, we have a Carnegie lesson that should already be in your binder called Every Graph Tells a Story. We've approached this lesson before. We looked at the graphs last week. We paired the graphs with their correct scenario. Currently, I have my graphs in ABC order, so it might help you to also have your graphs in ABC order so that we can quickly walk through the graphs. Let's take a look at some of the information. Now, you might have joined me for Zoom, I don't know, sometime last week, and we tried to go through this activity and it was very challenging. So I'm re-recording it so that you feel more confident with the material. First off, we've been working on all these key terms. So you've watched at least 6 or 7 Learn Zillion videos that should have helped you identify what these vocabulary words mean. 2 of the ones we're going to focus on today are discrete graph and continuous graph. Discrete graph can be summarized very quickly as being called counted. Things you can count. Continuous graph is something that is measured. Now on Match and Analyze, we already put the graphs together. We had Toy Rocket, Pool Party, T-shirt sales, Rainy Day, DVD and game rentals, and Fish Tank. On all of these graphs, on the previous video, we identified the y-axis and the x-axis. We went ahead and labeled everything here and here. We talked about why we graphed them in the way that we did. So we really already took care of 1 and 2 on the previous video. So we are here. So join me here. Discrete and continuous graph. You had an Ed Puzzle and Learn Zillion about these vocabulary words here. Discrete graph is a graph of isolated points, which means they're just pinpoints. You don't want to connect the graph because not every single number makes sense for it. Like you're not going to give somebody 2.1 of a cookie. Like that doesn't make any sense. You're going to either give them 2 cookies. You might give them 2.5 cookies, but it's really not worth it in most of these scenarios. So discrete graph is when the information doesn't make sense to be fractional. They're often counting numbers. Whereas a continuous graph has no breaks in it. A good example of continuous graphs involve time. Time often is dealt with continuous graphs because 1 minute, 2 minutes, 3 minutes, and you can boil it all the way down to seconds. And it's easier to make a continuum of it. Which graphs are discrete graphs and which are continuous graphs? So we need to just go through our graphs and identify who is discrete and who is continuous. All right, take your toy rocket. Time. So the rocket launches and then it falls down. Is this discrete or continuous? This one is a continuous graph. Next one, find pool party. Is this discrete or continuous? It's number of teammates and they're dividing up cookies. What makes more sense? If you said discrete, you are correct. Good job. Next, t-shirt sales. Number of t-shirts versus the total cost. Discrete or continuous? And ask yourself, would you buy only a portion of a t-shirt? Would that make sense? You wouldn't. That wouldn't make any sense. So this is a discrete graph. Very good. Next, rainy day. Discrete or continuous? Take note that the x-axis, the independent variable, is time. Time is often a continuous graph. DVD and game rentals. Discrete or continuous? Discrete. Fish tank. Discrete or continuous? Again, time, we're going to go with continuous. All right, now, let's revisit the questions here. Now, it's okay if you don't have this packet, but I do highly recommend that you take notes with the video so that when you have to do the follow-up questions, you have the answers in front of you and you can just click the correct answer from the Google form. So it wants to know which ones are discrete, which graphs. Discrete graphs were graphs B, C, and E. How come? The independent quantity the x-axis in each graph is an object measured by counting number. For example, things that were measured by counting numbers included teammates, t-shirts, and rentals. Which ones were your continuous graphs? Those were graphs A, D, and F. The independent quantity in each graph is time, and time can be represented by any rational number. I remember on Zoom we also ran out of space here. The independent quantity in each graph is time, and time can be represented by any rational number. So that was all of number 3. Number 4, which graphs represent equivalent ratios? How does the scenario inform you that the graphs will display equivalent ratios? How can we make equivalent ratios? I'm going to zoom out for a second. I want you to take a look at these graphs. When I think equivalent ratios, I think to myself they're looking for a line that repeats in a very systematic, predictable way. This one is linear, but it's going down, and it doesn't start at 0, so it makes me a little nervous that it would be equivalent ratios. I like this one a lot because it starts at 0 and it's very clearly linear. That makes me think we could make equivalent ratios. This one does not have equivalent ratios. This one's all over the place. This one's also a nice line, but it doesn't start at 0. So that one makes me a little nervous. This is not a line. And this is not a line. So when I look at my choices, the only one that feels like it could step up using equivalent ratios, which basically are equivalent fractions, would be DVD and game rentals. So we look at E and we say, contains equivalent ratios. We'd even be able to find a unit rate if we really needed to. So, DVD and game rentals contain equivalent ratios. So number 4, DVD and game rentals graph E shows equivalent ratios. Shows or displays equivalent ratios. The scenario states a unit rate. I can multiply by the unit rate to determine the total cost. So again, there's number 4. DVD and game rentals graph E shows equivalent ratios. Take a look at the shape of the graph. It is very linear. It goes through the origin. It steps up in a consistent way. That is equivalent ratios. All right, you're doing great, Dragons. Let's keep going. Consider the graph rainy day. We struggled with this one during Zoom. I think I found a way to explain it a little bit better this time. Assume that 2 hours after you left home, 1.5 inches of rain had fallen. Okie dokie. It says 2 hours after I left home, 1.5 inches of rain had fallen. So they're telling me that this right here is 1.5. All right. So in 2 hours, 1.5 inches had fallen. Let me look at that. One and a half inches had fallen in 2 hours. We worked on this math earlier, and we determined that that would be 7/500ths of an inch in 1 hour. All right. Now here's the thing. In order to make this a realistic comparison, we need to compare another 2-hour block. So this is what happened in 2 hours. So what happens in another 2 hours? So I can come over here and I can see I can start at 8 and I can go up to 10. And I can see that I climbed 1, 2, 3, 4, 5 blocks in those 2 hours, whereas I had climbed only 2 blocks or if you're counting from 0, but it's not, in those 2 hours. I climbed an entire 5 blocks. We could look at it a couple different ways. See, this graph doesn't start at 0, so it's a little misleading. It's saying that after 0 hours, you already had half of 1.5. It's saying from no time whatsoever to 2 hours later, 3/4 of an inch had fallen. Here, we're saying we've done more than that. So this was the climb here, from here to here. Short climb. But then we have a really steep climb here. Really steep. And when we made this right here, we kind of made the assumption that all 1.5 had fallen in 2 hours, when in fact I really think only 0.75 had fallen in 2 hours. I wonder what that would look like. Because that's really the change. We're not starting at 0. So let's take a look at it from that perspective. Let's do 0.75 divided by 2. There we go. So really, here, this is how much we're moving. So this statement here would only be true if we started at 0. But we didn't. So that's not true. This is true. At 0, we were here. At 2 hours, we were here. We did this short little climb. Now here, we do a giant steep climb. So in 2 hours here, how much did we grow? Let's take a look. If every 2 blocks is 0.75, every 1 block is 0.375. I'm saying I went 5 blocks. Okay, this is what I'm saying in the next part. On this portion here, this steep line can be represented by saying that I went this far in 2 hours. So how far did I really go in 1 hour? I went that far. I have that many inches. So this is the earlier part of the graph. Let's color code this so you can see what I'm saying. This part of the graph is earlier. This represents this climb. Versus this part of the graph, which happens later on in the day, represents this climb. This climb is much steeper. It is raining harder. You're accumulating more inches. Now let's look at the digits. I have 0.9 inch here per hour, which is almost a full inch, where I only have 0.375 inch here per hour. That's not even half an inch. So we can either look at the steepness of the line to determine when is it raining harder, or we can actually nitpick the numbers and calculate them out using our calculator and see that the blue is definitely falling faster, harder, gaining more inches quickly. More quickly. That's how you analyze that one. That is everything about number 5A. They want to know, write an inequality statement in terms of time to represent when the rain stopped. When did the rain stop? All right, let's take a look at that. The rain stops here. You trickle down, and that number would be what? What number would live right there? When does the rain stop? If you said 11, you are correct. So, rain stops when time is greater than what number? 11. All right, and we did this answer. We wrote it on graph. So we did 5A. We wrote it on the graph. I showed you all the complicated numbers. 5B, the rain stops after 11 hours. We're going to keep going. Consider the graph in the toy rocket scenario. Toy rocket. The rocket reaches a maximum height of 256 feet. That would mean that this dot here is 256. Describe the shape of the graph. I would say the graph is not a straight line or made up of straight lines. It is the curve that goes up, reaches a highest point, and then returns to the x-axis. It has an upside down U shape. So, the shape of the graph. not linear. It has an upside down U shape. Why does it do that? I mean, you could just picture a little rocket ship soaring up, and then it loses all its momentum, and then it zips down. It takes the arc of the flight. Write an inequality statement in terms of time to represent when the rocket was rising into the air. So he rises all of this part. He's up, 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 up. I'm flying, I'm flying, I'm flying. And then he plateaus. So T, he's rising, rising, rising until when? When does he stop growing? I feel like he stops growing and rising here. That is the tippy top point. So, anytime the time is less than 8 seconds, all of this area, the rocket ship is rising. T less than 8, the rocket ship is rising. Last one. Consider the graph of the t-shirt sales scenario. Suppose there is a minimum order total of $100 when you're ordering the t-shirts. Write an inequality statement for the number of shirts N that must be ordered to meet the minimum order requirement. All right, find your t-shirt graph. In this scenario, it tells us that no matter what we do, there's a $25 design charge. That means before I even order, I'm at $25. Now you need to take a really close look at the increments here or we're going to mess this up. If this is 25, what is this line here? This is $12.50. This next one is how much? It's $37.50. I'm going to prove a point here in a second. And then this one here is how much? Should be $50. So then another two would be $75. And then another would be $100. $100's way up here. Now it says we need to spend $100. Suppose there is the minimum order when you order. Write an inequality for the number of teachers that must be ordered. I can go over to $100 and I can already see the answer. I suspect the answer to be 12. Just by using the graph. But now I need to write it as an inequality. I'm going to teach you how to do that. We know that there is a service charge. So no matter what we order, we have to pay $25. No matter what we do. We know we need to spend a minimum of $100. That means we're going to spend either more than or equal to $100. The part we don't know is t-shirts. That's where we're going to put something here. According to our graph, we need to determine about how much each t-shirt costs. Here is how I'm going to teach you how I figured it out. If 2 t-shirts was $37.50, I know the temptation is to say, oh, $37.50 divided by 2 gets me the price per shirt. But it doesn't. You need to do $37.50 minus the $25 fee. $37.50 minus my $25 fee means 2 shirts cost $12.50 to make. If 2 shirts cost $12.50, How much is one shirt? $6.25 per shirt. It costs $6.25 per shirt, N standing for shirts, and the $25 fee. Now, we studied very briefly two-step equations inside a foldable during Zoom meetings. I can isolate this variable N. Remember, this represents the price multiplied by the number of shirts ordered plus the setup fee for design greater than or equal to the $100 minimum requirement to order. Here's how we're going to isolate this. First, we're going to subtract 25 from both sides. That creates 0. We've got $6.25N is greater than or equal to $75. Now we're going to check out how these are connected here. $6.25 is multiplied by N. So in order to get N alone, to isolate the variable, I have to do the inverse operation, which is to divide. 625 over 625 creates 1, so I really have 1N. And the 1 is unspoken. It doesn't really need to be written. And I need to do the same thing to the other side of the inequality to be fair. We're going to pop out our trusty calculator. $75 divided by $6.25 is 12. You must order 12 t-shirts. At least 12 t-shirts. And we knew that because we already proved it from the graph. But now I proved it mathematically using an inequality. You've done a great job. Thank you for joining me for the video. You get points for watching the video, and you get more points for answering the questions correctly. I'll see you soon.